Welcome to this instructional video to replace Friday's class, February 15th, 2019. Our goal today is to learn about the remaining families you need to know for the exam coming up next week. So let's meet the families. The first family we want to talk about are ketones. And ketones have this general formula. By the way, all the families have a general formula. And you see this R. R means rest of the molecule, which is usually, but not always, a hydrocarbon. And so for a ketone, think about this. Look for our old friend, the carbonyl. By the way, the carbonyl is going to be in a lot of different families today. So you need to look for the carbonyl and then look what's around it to figure out which family you are dealing with. Okay? So with a ketone, there we go. We're looking for a carbonyl and then two carbons attached to it, typically. Okay, that's kind of what we're looking for. Again, let me just make a big point of this because this is important. This is carbonyl, and what's attached to this carbon of the carbonyl will dictate what family you're dealing with. Okay? With ketones, look for two carbons attached to the carbonyl. So if we look at a fairly large molecule, progesterone, which is a sex hormone, let's look and see, oh, I see a carbonyl carbon right here. I see a carbonyl. This must be one of the families that I have to know. Well, what's around the carbonyl? Well, look at this. There's a carbon. There's a carbon. So that tells me this is a ketone. R, C double bond O, R, or carbon, C double bond O, carbon. This makes this a ketone. Look up here. There's a carbonyl. What's attached to that carbonyl? There's a carbon. There's a carbon. Look at that. This is going to help us classify this as a ketone. What else could we classify progesterone as? Well, there's a carbon-carbon double bond, so I think another classification would be alkene. Okay, there we go. There's ketones. Aldehydes. Well, it's slightly different. R, C double bond O, hydrogen. If you have a hydrogen connected to a carbonyl, you have an aldehyde. That's a completely different family. And so I guess what you're looking for is the carbonyl, some hydrogen attached to it, and then usually another carbon attached to it. Okay? Well, let's look at a molecule. Now this is cinnamaldehyde, the main component of cinnamon. Now aldehydes are mostly pretty nasty molecules. They smell bad, they're pretty toxic and dangerous, but there's some aldehydes that are quite lovely, and we love, and most people, not all, love cinnamon. And cinnamon is an aldehyde. And how do we know that? Well, there's our carbonyl carbon. There's a carbon attached on this side, but oh, look at this. There's a hydrogen attached to that carbonyl. Is this a ketone? No. This is an aldehyde. One classification of this molecule is aldehyde. What's another? Oh, well, that makes it aromatic. That's our old friend, the benzene ring. And this is a double bond, a standalone double bond. So this makes it an alkene. So again, we need to be thinking about being able to classify molecules based on the families, the organic classifications. And again, we're going to be working in hydrogen bond donors and acceptors. I didn't go over that on this page, but we may do this as we move along. So let's meet another family. Carboxylic acid. Ladies and gentlemen, there you go. Here is our carbonyl. Here is our carbonyl carbon right here. And you might say, well, okay, it's got a carbonyl. Is it a ketone? Well, R, C double bond O, O. No, no ketone. Oh, is it an aldehyde? No, because it's R, C double bond O, Oh, it's not C double bond OH directly attached to this carbon of the carbonyl. This is a carboxylic acid. And again, I didn't do it on page 1 necessarily, but we can start putting in these lone pairs. It's going to be helpful. Probably the most famous carboxylic acid is vinegar, which we're going to name, well, the name of this is acetic acid, and we'll worry about naming later. This is really the main component of vinegar, and you cook with vinegar. And then I had laryngitis really bad a couple of years ago, and I used apple cider vinegar to help clear up my laryngitis. And so that's a carboxylic acid. Well, what are some other important carboxylic acids? Well, a lot of us need to take medicine for pain. And one of the common ones is Advil, which really is ibuprofen. And Advil is another non-steroidal anti-inflammatory drug, along with aspirin and naproxen, which we've mentioned in class. Ibuprofen is another one of these classes of drugs. And if you look at the structure of ibuprofen, here we go. I think these carbonyls are landmarks, because that kind of helps you get started classifying the molecule. There's a carbonyl carbon. There's a carbon on this side, but oh, wait a minute. There's an oxygen attached to this carbonyl carbon. It can't be a ketone. It can't be an aldehyde. Since it's OH, C double bond OOH, it has to be a carboxylic acid. So this makes this molecule a carboxylic acid. And then we can go looking for other classifications. This is our aromatic benzene ring, and that's probably the best two classifications for this molecule. Let's take some time and talk about donors and acceptors for a moment. If we look at ibuprofen, how many donors do we have in the molecule? Well, there's just one hydrogen right here attached to FON or S, so there's one donor. And then ibuprofen has 4 acceptors. All right, so why do we care about carboxylic acids? Well, carboxylic acids play a number of roles in our life, and specifically in the molecule ibuprofen for this particular page of notes. All right, you know what's next. We've got another family to meet. Esters. Not ether, ester. What do you have? You have this landmark carbonyl, but this is a different arrangement of atoms. Ladies and gentlemen, this is a unique arrangement of atoms than we've seen before. An ester is an R, C double bond O, O, R. If this was H right here, it'd be a carboxylic acid. It's not. It's another R group. So you're looking for a C double bond O, O carbon. It's kind of what you're looking for here. Okay? So, let's look at some molecules and see if they're esters or not. Well, let's look over this molecule to the right, or the middle, in the middle, I guess. This is a molecule that gives bananas its smells. It smells like bananas. And so, if we locate the carbonyl, which is our landmark, one of our landmarks, we see there's a carbon next to that carbonyl. Oh, there's an O. There we go. It's C, carbonyl, and then that's an oxygen, and then there's another C. Ladies and gentlemen, this is our arrangement for an ester. Is it a ketone? No. Is it an aldehyde? No. Is it a carboxylic acid? No, because this is not OH. Is it an ester? Yes. And again, this gives us, this molecule gives us the taste and smell of banana. So let's spend a few minutes on this molecule. Let me put in the lone pairs. So let's just kind of stay with this one. Can this molecule H bond with itself? Well, let's look at it. You have to identify donors and acceptors to answer this question. Hydrogen bond donors, hydrogen bond acceptors. The number of donors in this ester, this banana ester, is 0. Acceptors happen to be 4. Again, I've been begging you to, when you see a molecule and I'm asking you questions about it, to put in your lone pairs right away. I think that's the best way to go. So as we look up here, can this molecule H bond with itself? That's a big no. There's no donors. So if you had 2 of those molecules, it could not hydrogen bond with itself. Can this molecule H bond with a carboxylic acid? It's like, oh, well, hang on a second. We know the carboxylic acid looks like this. Aha. And so if we do a little quick drawing of it, donors 1, acceptors 4. Okay, the carboxylic acid has a donor. Our banana ester has many acceptors. So the answer to this is yes, it can. Okay, you got to know the families. All the families have a unique arrangement of atoms, and they all fit the bonding rules that we have clearly established. The molecule on the right is our old friend aspirin, that we already said was a non-steroidal anti-inflammatory drug. If you look at this molecule, I think you should landmark the carbonyls. Okay, and then I'm going to identify any carbons attached to the carbonyls, or any other carbons around it that might help me figure out what this molecule is. It looks pretty clear to me that aspirin is a carboxylic acid based upon this right here. C double bond O, OH. This right here makes aspirin an ester, not an ether. Okay. R, C double bond O, OR. That's an ester. That's an ester. All right. You just got to practice this classification. There's practice on canvas of recognizing these molecules. All right. So let's look at another one. The next one is called an amide or amide, depending upon how you want to say it. Potato. Okay. Amide, amide. And it has this general formula. Guess what? Another carbonyl. Sorry. Here we go. So you look at a carbonyl, and then attached to that carbonyl is an R group, which is probably going to be a carbon directly attached, but also attached to the carbonyl is a nitrogen atom. And then that nitrogen has 2 bonding positions off of that. That can be hydrogen or R. All right? So let me just do this. So the little black dot here, I don't want to do that. Hang on a second. So in this position can be R, a hydrocarbon fragment, or H on an amide. Okay? So if we look at a fairly complicated molecule like Lipitor. Now Lipitor is a statin drug used to lower people's cholesterol. It saves a lot of lives. The question is can Lipitor be classified as an amide? And then what other classifications can it be? Well, again, I'm going to landmark my carbonyls, and I'm going to look at carbons that might help me answer this question. After doing this, I see that this looks like an R, a carbon, C double bond O, N, and then there's an R and an H. This tells me that's an amide. That fits the general formula for an amide. Okay? Look over here. R, C double bond O, OH. Carboxylic acid. Now, those are two important families. There's some other ones that we should be able to look at based on our previous knowledge of families. We would call this part of Lipitor alcohols. You have an ROH and an ROH. Okay? And then you've got a lot of benzene rings. So you've got aromatic as well. So there's a benzene ring. You get a benzene ring. You get a benzene ring. So that's aromatic. So a lot of molecules, important molecules, have multiple classifications. And I'm asking you to be able to look at a structure and classify it based upon the families. And you do that by knowing the general connection of the atoms that we have been going over. So, amides are unique from esters, which are unique from carboxylic acids, which are unique from aldehydes, which are unique from ketones. And those are all the ones today that have contained our friend, the carbonyl group. All right? Well, let's practice a question here. This is the kind of question that you're going to see next week. So draw the structure of an amide with 3 carbons and 1 H bond donor. Wow. So I'm giving you some information in the question. You have to make it an amide. So we know right away that you have to have this fragment. Okay? R, C double bond O, N, and then off the N can be an H or an R group or some type of hydrocarbon fragment. So we only can use 3 carbons total, and we have to have 1 hydrogen bond donor. Well, how would I do this? I'm going to put the fragment that I know is there. Okay. The only way to get a hydrogen bond donor off of this fragment is to have it coming off the nitrogen, right? The oxygen of carbonyl is all happy. It's full. Don't worry with this oxygen. It's got 2 bonds and 2 lone pairs. The only way, ladies and gentlemen, the only way to get a hydrogen bond donor off this amide is to make it off the nitrogen. Okay. I have satisfied the fact that we have 1 hydrogen bond donor. I just need to go back and make sure we've got 3 carbons. I've already have 1 carbon shown, so all I have to do is add in 2 more. I didn't give you a formula here. I gave you 3 conditions. An amide, 3 carbons, 1 H bond donor. Does this molecule fit the question, fit the criteria I ask you to meet in the question? I say yes. And you may see this drawn, and you can draw it this way if you wanted to. Whoops. That's kind of the condensed formula. Hey, that's an amide. That's definitely an amide. And it has 3 carbons. In fact, if you look at it, the number of donors is 1, which is what I asked you for. The number of acceptors is 3 when you put in all lone pairs. All right. We've got 1 more family to learn. I know, there's a lot of them. Sorry, that's the way it goes. The last family is called amine. Now, in the playbook, I say there's different families of amines, or different there's different subcategories of amine. There's primary, secondary, and tertiary amines. For right now, I'm not going to ask you to subclassify it. I'm just interested whether or not you can know if a molecule is an amine or not. Don't worry about primary, secondary, or tertiary. So this is not now. We'll get there, but not now. So a lot of people, and some of you on Thursday, are going to confuse this. It's going to be a tragedy. I'm trying to warn you. People confuse amine and amide. I know it sounds kind of alike. It's spelled very much similarly, but D is not N is not D. It's an amine, not an amide. Amines do not have a carbonyl attached directly to the nitrogen. So what you have is our nitrogen with one lone pair and 3 bonding positions. And you know this because that's what we said previously of how nitrogen likes to bond. So this orange dot can be H or R. Let me say it this way. It can be H or C, but not C double bond O. Because if it's C double bond O, that's going to make it an amide, not an amine. Okay? There's a whole bunch of important, biologically important amines. Heroin's an amine. Cocaine is an amine. Opioids are amines, pain relievers. One that you may be familiar with, heard about, is methamphetamine. And this is kind of a picture of called meth mouth, people who abuse crystal meth, methamphetamine. So if we look at the structure of methamphetamine, I hope you see that this is a pretty small molecule, but it carries a very powerful punch. And I'm just going to put this in the category of something we want to avoid. Okay? Well, how do I know methamphetamine is an amine? Well, it's got amine in the name, but we're not worried about names. When I look at this molecule, I want to put my landmark for carbonyls. I don't see a carbonyl, so I'm going to have to not do that. But I see a nitrogen, and so I feel compelled to put my lone pair. And so I see a nitrogen with 3 bonds and 1 lone pair. Ladies and gentlemen, that is always an amine. How else can we classify methamphetamine? Well, this is a benzene ring, so this is aromatic. So we're going to meet a lot of different amines that are important. This one is, I guess you would call it important because it's a huge problem, especially in western Kentucky. So, alright, what else can we do with this? So, what if I ask you this question? Draw the structure of an amine. There we go, there's a clue. You know, working these word problems, maybe I've mentioned this, is like walking up on a crime scene. You got to solve the crime. There's evidence left at the crime scene. Well, a very important piece of evidence here is that I've asked you to draw an amine. So all of a sudden, you know it's got to have that. Okay, you know that. With the formula below, and I haven't given you the formula, but I will, C4H11N. Okay, you got the formula. That's your second piece of information, or clue. And has 0 H bond donors. Okay, there's 3 things you have to do. Draw an amine, it has to meet this formula, and you can't have any hydrogen bond donors. So how am I going to do this? Well, here's the deal. I'm going to draw this because I know that's in there. Ladies and gentlemen, am I going to have any hydrogens directly attached to this nitrogen? Because I said up here in amine, these orange dots off of the nitrogen can be hydrogen or carbon. Okay? But as soon as I put one hydrogen directly attached to the nitrogen, I have a hydrogen bond donor, and that's not allowed in this question. So I know that I'm going to have to put carbons around this nitrogen. Okay? Now, if I just stopped here, that wouldn't be good either, because I have to have 4 carbons. Well, it's your choice. You can put another carbon on any of the existing carbons I've drawn here. You can't put that carbon on nitrogen because you've already have 3 bonds to the nitrogen. So I'm going to do that. Does this work? Well, I'm feeling pretty good about this. Whoa, almost missed a hydrogen. Alright, so, is it an amine? Yes, it is. Does it meet the formula C4, 1, 2, 3, 4, H11, 3, 6, 9, 10, 11, and no hydrogens directly bonded to FON or S? Hey, that's it. And so, a condensed way to draw this, I'll take this, that's fine. Just make sure if you're going to draw a line bond, I need to see all the bonds though, okay? But this is the condensed formula. There we go. That works. I know there's a lot of families, but again, we still have a pretty good bit of time before the exam, and so I've given you some practice on looking at structures and identifying the various families you need to know. And if you want like a summary of that, the playbook tells you which families you need to know. Okay? Well, before I wrap this up, let's do this thing we do where I give you some structures and you give me some information that you can get from the structure. Well, I want to know about this molecule here on the left. I need to know several things. What is the formula of this thing? Well, it looks like to me we have, again, I'm not sure if I should draw in all the hydrogens or not. Maybe I should let you do that. I'm going to let you do that because I think this is C4 H9 ON. That's the formula. What else do we need to know? Well, we need to know the classification. Here's a landmark carbon. It's the carbonyl carbon. That makes it my landmark. Okay? And if we put in other carbons, okay, it looks like we have a C double bond O, C. What is that? This makes this a ketone. And I know what you might be thinking. Well, there's a nitrogen and there's a carbonyl. Isn't that an amide? And in this case, the answer is no, because the carbonyl carbon is not directly bonded to the nitrogen. So this is not an amide. This is a ketone. Okay? But you're onto something because you have a nitrogen. Okay, sorry about that. You have a nitrogen in the molecule, and this looks like you've got a nitrogen with 3 bonds and 1 lone pair. Hey, that's an amine. So the classification of this is ketone and an amine. Right now, I don't care for you to tell me if it's primary, secondary, or tertiary. That's later. Okay? Well, let me go ahead and put in all the lone pairs. That's something I should have done right away, but I didn't. See? When we look at donors and acceptors, it looks like the number of donors here, 2, because there's 2 hydrogens directly bonded to this nitrogen, and acceptors, 1, 2, 3 lone pairs. Alright? Well, my little marking of the carbons a while ago actually helps us with what's next. The red carbon. The red dot I've been putting on carbonyl carbons makes this a what type of carbon? In fact, it's unique. It's unique in this. There's only one carbon that just has a total attachment to 3 atoms. So this is our trigonal planar carbon, and there's just one. Ladies and gentlemen, a carbonyl carbon is always trigonal planar. A carbonyl carbon is always trigonal planar. Just like all the carbons of carbon-carbon double bonds that we've seen, for the most part, are trigonal planar. Okay? Well, what's left? Well, you got all these blue dot carbons. What are these blue dot carbons? Well, if you were to fill in the hydrogens, I'm not going to do that here, you would see that each of the blue dot carbons is attached to 4 atoms. That makes them tetrahedral. So there's 3 tetrahedral, 1 trigonal planar, and there's no linear carbons. All right. Let's do this one over here. In fact, I think you should stop the video and answer all these questions and then see what I say. Okay? So, and I'm not going to put in all the hydrogens here. I'm going to let you do that. I'm going to say, based upon my knowledge of how this works, I can tell you the formula here. Okay? So this is going to be C8H12O3. Okay? If you fill in all the hydrogens where they need to be, you should have 12. There's 8 carbons and there's 3 oxygens. I'm going to be a good accountant of electrons. I think you should do this immediately. Every time you see a molecule, put in the lone pairs. I've done that. And so, well, I guess we could do that next. Okay, how many donors? How many, in this molecule, how many hydrogens on FO, N, or S? Well, I just see 1. That one right there. Some people like to say, look at this carbon and try to call it a donor. Do not do that. Do not do that. It's on carbon. Hydrogens have to be on FO, N, or S to be a donor. So the number of donors, 1. The number of acceptors, 1, 2, 3, 4, 5, 6. An acceptor is a lone pair of electrons. Okay? What about classification? Well, I'm going to go ahead and put my red dot landmark for carbonyls. And hey, I already know I have 2 trigonal planar carbons because carbonyl carbons are trigonal planar always. But we'll get back to that. So let's put in other carbons that might be of interest to us right now. It looks like to me we've got an RC double bond OH. That screams very loudly aldehyde. I'll look at this. I see a C double bond OH. That tells me this molecule is also a carboxylic acid. And that's probably the best 2 classifications. If you told me cycloalkane as well, then I would take that, because it is the cyclohexane, cycloalkane ring in this thing. But I think the 2 major ones that distinguish this molecule is the aldehyde and carboxylic acid. All right. Well, we need to keep on going with the carbons, so I'm going to label the rest of the carbons, and I'm making them blue because these carbons all have the same shape, because I know that the blue carbons are all what? Well, I haven't drawn the hydrogens in. You need to do that. But every blue carbon shown is attached to 4 atoms. So they are, I'm not sure why I just did that, tetrahedral. So 1, 2, 3, 4, 5, 6. And then we've got the the only trigonal planar carbons in this molecule. That's not always the case, but in this molecule happens to be 2. All right? And wow, I think that's kind of what we've been doing with these molecules. Ladies and gentlemen, we've met the rest of the families. We've seen their connections of atoms. The connections of atoms make the families unique. You need to be able to look at a given molecule and classify it based upon the families that we've talked about. Okay? We have a variety of families. You need to be able to look at a molecule and give it a classification. Of course, formula. Can you give me the formula? Donors and acceptors, and tetrahedral, trigonal planar, or linear. There were no linear carbons in this molecule. I'm going to be honest with you. When it comes to linear, in our world, usually it's going to be a carbon-carbon triple bond that's going to give you a linear carbon. Okay? I don't see any carbon-carbon triple bonds here, so I didn't have to worry about that. Ladies and gentlemen, there is no quiz based upon today's video lecture. We are done with Chapter 4. I hope you spend this weekend studying the notes, studying all the practice things that's on Canvas, all the challenge problems I've given you. Oh, and by the way, there is a challenge problem based on today that's on Canvas in today's module. So yes, there is extra practice for today. There is a challenge. There is a challenge. There is no quiz. And then this weekend, look at the challenge problems. Look at the suggested problems in the chapter. Again, Canvas, there's practice doing ionic formulas and ionic names based on formulas. There's practice doing molecular formulas. There's practice hydrogen bonding. There's practice classifications. All these things you need to be doing to study for the test next week. Monday, I've reserved as a review day for us. I've got some more questions for us to answer on Monday. Next Tuesday's lab. Wednesday's the mock exam. Thursday, boom, exam number 2. I have one last question for you. Are you ready? Have a good weekend.